last time. So where we left off last time, we were talking about pH and its effect on solubility. We had started talking about KSP, which was, we had gone through some sample problems showing how common ions affect solubility, right? There's an example here where we had calcium fluoride and we were trying to determine how soluble calcium fluoride was. Oops, let me not in full screen mode here. There we go. Example, we're looking at calcium fluoride, trying to determine how soluble calcium fluoride was in the presence of either having, calcium ions present from the calcium nitrate or fluoride ions present from the sodium fluoride. We went through and we used, the ICE tables, so very similar to what we've done before, and used an ICE table showing what happens when you have extra calcium present and how it affects the overall solubility of the solution, because we would use the KSP, the solubility product constant, in order to determine its solubility. So we went through and just simply solved for X to determine the solubilities. We did this again for both calcium fluoride and sodium fluoride. All right, and then we started talking about how pH is going to affect solubility. Right, so we briefly introduced this. So if soluble substance has a basic anion, it will be more soluble in an acidic solution. And because it says, remember that buffers control pH. So when a buffer is used, there's no change in concentration of the hydroxide ion. So let's see when they're talking about here, and this is the last slide that I just covered just before we ended last class, where, right, we had this example here. We had lead fluoride, solid lead fluoride sitting down in the bottom of the flask. And there were, a few fluoride ions and a few lead ions floating in solution. If we added an acid to this solution, right, this solution, the lead fluoride that's in solution, that's going to react now. So the lead fluoride, or I should say the F minus that's in solution, is going to react with the proton that you add in an equilibrium fashion to give you HF, right? So what that does is you have the lead fluoride plus, oops, not plus, in equilibrium, right? Lead fluoride that's in equilibrium with the lead ions plus fluoride ions in solution. This is the KSP, right? And this is the minus of the Ka equation. It's a really bad K. Oops, too many erasers. So minus the Ka, right? So you can see what ends up happening is when you add protons to solution, they react with the fluoride. So it's going to react with fluoride that's produced here. So this fluoride concentration is going to decrease. And when that happens, the equilibrium shifts to the right and it dissolves more of the lead fluoride. So that's why when we're looking at, adding, how the pH affects the solution. Whereas in the example on the right, I minus plus H plus, and if we wanted to look to see, does this form HI? The answer is here, that reaction doesn't occur. And the reason for that is because this is a strong acid, right? So there is no Ka, whereas in this side we have the weak acid, right? And there's a Ka and equilibrium associated with it, right? This reaction only goes completely in the reverse direction because it's a strong acid is fully dissociated. So this doesn't affect the equilibrium solubility or the KSP of the lead iodide. All you end up with is extra protons in solution. Right. So we'll work through some sample problems. It says, which of these substances are more soluble in acidic solution than in basic solution? So if we look at nickel hydroxide first, right? So that's what we're going to do is we're going to identify ionic compounds that dissociate to produce a basic anion, as these are especially soluble in acidic solution. So we're going to look at nickel hydroxide first. It's more soluble in acidic solutions because of the basicity of the hydroxide ion, right? The H plus will react with the hydroxide ion, forming water, right? So this is what we're showing here, is if we have our nickel hydroxide here, and it dissociates to give us nickel ions and hydroxide ions. And when we add protons, right, the protons are going to react with the hydroxide ions that are being formed here, right? So these two hydroxide ions are then going to react with two protons to form two water molecules. And so you can see overall, when you add these two equations together, when the nickel hydroxide reacts with protons, it forms nickel ions plus water. So you can see basically you're able to increase the solubility of nickel hydroxide in an acidic solution. So if we look at calcium carbonate, right, it's going to dissolve in an acidic solution because the carbonate ion is a basic anion, right? Same exact thing, right? Calcium carbonate dissociates to give us calcium ions plus carbonate ions. If we then take that carbonate ion, react it with two protons, it forms carbonic acid. And there's actually, under many acidic solutions, this typically would be all that would happen. But carbonic acid, we've talked about before, carbonic acid is basically a solution of carbon dioxide and water, right? So there's an additional equilibrium step that happens when we react carbonic acid. It dissociates to give us carbon dioxide and water. So you can see overall, just like the previous one, the carbonate anion cancels, the carbonic acid cancels, and we end up with an overall calcium carbonate reacts with protons to give us calcium ions plus carbon dioxide and water. So you would have gotten to the point here where you could have just drawn this as H2CO3, but the problem would have been is that carbonic acid actually isn't stable for very long in solution, and it typically falls apart. All right. If you had and what they're stating down below is there's actually a second two individual steps here, because the carbonate ion initially reacts with one proton. To give us HCO3 minus, which is the bicarbonate ion, and then that bicarbonate then reacts a second time with another proton to give us the carbonic acid. So there's actually two different steps. So if you only added a very small quantity of protons, this acid in solution, you would only have the first step occurring, and you'd end up with a bicarbonate ion, and you'd have this mixed anion because you'd have the calcium ion would still need to be coordinating at least one bicarbonate ion. So this reaction needs a large quantity of protons present in solution. All right. The solubility of barium fluoride is enhanced by lowering the pH, because fluoride is a basic anion, right? And same here. We take barium fluoride, it reacts it has a KSP to produce barium ions plus fluoride ions. These fluoride ions, because they're the conjugate base of a weak acid, will react with protons to give us the HF. And you can see here again, the fluoride ions cancel, and we end up with an overall equation where barium fluoride reacts with protons to give us barium ions plus 2HF. So if you know it's a basic anion, so if you're trying to figure out if fluoride is a basic anion, what you would do is say, well, what is its conjugate acid? Conjugate acid is HF. And what is the Ka of that conjugate acid? If this Ka is a, if you have a Ka, then you know you have a weak acid, so then you have a basic anion. Whereas if, say, we had iodine, right? Iodine, the conjugate acid is Hi. And in this case, you say it doesn't have a Ka because this is a strong acid, so this is not going to be a base. It's a good question. You know, the same thing, right? If we had HSO4 minus, right? And you say its conjugate acid is H2SO4, which is a strong acid. So you say this is going to be a weak base. It's not a basic at all. So anything that's a basic, almost everything except for anything that's the conjugate of the strong acids. It's a really tiny list of strong acids that we're working with. All right. So the solubility of silver chloride is unaffected by changes in pH because the chloride is the anion of a strong acid and therefore has negligible basicity, right? So it's the same thing here, right? Where we have Cl minus, its conjugate is HCl. This is a strong acid, so this has no basicity, right? So it's not a basic ion whatsoever. Right. So complex ion formation. So metal ions can act as Lewis acids and form complex ions with Lewis bases in the solvent. The formation of these complex ions increases the solubility of these salts. So what are we talking about here? We're forming a complex ion. And complex ions formation are kind of a unique solution situation. If we take, and look here at the various silver complex ions, right? We're doing is we're taking silver ions and we're reacting them with ammonia. And you can see what we end up forming is this silver complex. We have and the reason it's called a complex ion is because of the fact of if we look at the ammonia here, right, NH3, it's neutral, right? It's a neutral molecule. And since it's a neutral molecule, what we're forming is we have the lone pair, let me draw it across the top here, right? We have our silver plus ion. It's reacting with the lone pair present on the ammonia. Right? So we're forming this new, I just want the first one adding on here. We're forming this new silver nitrogen bond. Right? We're now essentially, we've transferred the positive charge. You could do a formal charge calculation. Then the positive charge has been transferred to the nitrogen atom, right? Because the lone pair is now forming a bond here. Oops. And why does it do that? And we have this complex that occurs. And then, right, we have another second ammonia molecule react. We're having the same thing here occur where we have another silver ion reacts with the same silver ion reacts with another ammonia molecule. So we end up with a positive charge there. We end up with another positive charge because I'm sorry, only one positive charge. No, it's not. no, it's not. I'm sorry. True. We end up with another positive charge on this and then negative charge on the silver. If you calculate the formal charges, so overall the molecule, right, ends up being only one positive charge because the negative and the positive charge just cancel each other out on one side. But what you form is this complex, and a complex what we're talking about is this sharing, right? It's a sharing of electrons from a neutral molecule. So when we're talking about complex ion formations, it's because of the fact that we're sharing, making bonds with electrons from neutral molecules, and not. Well, I guess it's not necessarily just that it's a neutral molecule. It's the fact that we have sharing of electrons that are. Let me step back a little bit because it's not just the neutral molecules. They're from molecules. What's the word I'm trying to say? It's not just that it's neutral. It's the sharing electrons almost. I'm not sure exactly what it's to form from. From several. Let me see. Let me change my term. From several molecules. From several molecules to form a new charged molecule. It doesn't have to be neutral. I have to step back a little bit. So you see what happens here is, right, we end up forming, we've shared electrons, and we have this new complex ion. So the ion is, you could see, if I've drawn out the ion up above, and you can see there's two positive charges and a negative charge, but the overall charge on that ion is just, +1. So it's a complex ion because of these, different groups being attached to make this more complicated or more complex ion that exists in solution. So you can see down below, we have the silver, right, reacts with two cyanide ions to give us silver cyanide with an overall negative charge. You could, draw the exact same sequence here, and you'd see that you'd have the negative charge from the cyanide, extra negative charges coming from the cyanide this time. S2O3, you can end up with an overall -3 charge. You can see that you create these new ions, right? These are all new ions that are being formed on the right-hand side of the equation that are then complex with something else, right? Because this silver ion here, let's just say this was silver nitrate, right? So there's still a nitrate ion floating around in solution. So we've created a new ion, a new positively charged ion that's a counter ion to the nitrate. You can see here, there are numerous varieties of complex ions that can be formed. Right, we can make a complex ion. We take aluminum, make aluminum hydroxide by reacting, 3 aluminum molecules. 3+ aluminum molecule with 4 hydroxide ions. You can end up with an overall negative charge. Cadmium in the 2+ state reacted with 4 bromides and end up with this cadmium Br4 with a 2- charge. Right, chromium, the same thing with 4 hydroxides, end up with this chromium hydroxide anion. And cobalt thiocyanate reacting to give us this complex cobalt thiocyanate anion. Right. Another question. Lewis bases, are you asking for? They are going to be Lewis bases just because essentially anything that's basic will be grouped into the Lewis base category. So yes, you could suggest that you're sharing electrons from Lewis bases. They could just be simply hydroxide ions. So sorry, just saw your comment. All right. So there's a lot more complex ions. You can look through the complex ions on this page too. But what's associated with this is a new equilibrium constant, Kf, right? So we have a new one. We have Kf. And remember, all this is products over reactants, right? We have our product, our complex, divided by our reactants is the formation. So the equilibrium constant of formation, that's all the Kf is. So it's just a new equilibrium constant that's based on this chemical equation. All right. So if we look at how complex ion formation affects solubility, you could see how, in this case, so many constants. Yes, welcome to the world of equilibrium. They all mean, just don't be frightened by the number of constants. They all mean the exact same thing, right? It's just products over reactants, and they're just each special cases to, designate a specific situation, right? All this is a fancy, complex, formation constant. It's, describing the reaction to form these new complex ions. Right? So we're looking down below here, and this is an overall interesting reaction because silver chloride, if you recall back when we were talking about silver chloride and last semester, we learned that silver chloride wasn't soluble. But if we add ammonia to the solution, very funny, Annie. If we add ammonia to solution, you can see here that the ammonia actually dissolves some of the silver chloride. And the reason for that is because it's forming this complex ion, the silver ammonia complex ion. And the interesting thing is, that if you were to just simply have silver chloride in solution, silver chloride wouldn't dissolve at all. But adding a little bit of ammonia to solution, and suddenly you form this complex ion that's able to dissolve the silver chloride. Right? So this is what they show, in the tube. If you add ammonia, it'll react with the silver ions. So slowly over time, these complex ions are formed in solution. Eventually, all of the silver is dissolved, and you end up with a complete solution of silver. These complex ions are silver floating around the solution. And, we were looking at the KSP, right? The KSP of silver chloride is a really tiny number, 1.6 times 10 to the minus 10. So extremely tiny number. So whereas in the presence of ammonia, the solubility is greatly increased because the silver ion will form a complex ions with ammonia. And here's kind of a breakdown of the equation. I'm going to go quickly through this and, discuss. So it says calculate the concentration of silver ions present in solution at equilibrium when concentrated ammonia is added to a 0.010 molar solution of silver nitrate to give an equilibrium concentration of ammonia of 0.20. Neglect the small volume change that occurs when ammonia is added and assume silver nitrate fully dissolves in solution. So here's the complex ion chemical equation, right? So if we addition of the ammonia to silver, right, adding silver with ammonia gives us the complex ion formation. It's got a Kf of 1.7 times 10 to the 7th. Now, remember what our KSP looked like, right, of silver chloride. The Kf is an extremely large number, right? We're talking yes, right there. Right. That's our Kf for this equation. Is extremely large. does the silver need to dissolve first? In this example, it's already dissolved. In the case of silver chloride, it would be a slower reaction, but it would occur over time. So like in the previous slide here, this is reacting with silver chloride. So this is rate limited by the ammonia ions coming in contact, right? The ammonia ion has to come in contact with the surface. Right, so here's the ammonia ion has to come in contact with the surface in order for the reaction to occur. So it's going to be a slower reaction, even though it has a high Kf, so you'd have to let it stir for a while. All right. So we're asked to determine what concentration of silver ion remains uncombined when ammonia concentration is brought to 0.2 molar in a solution originally 0.01 molar in silver nitrate. So you assume silver nitrate is completely dissociated, giving 0.1010 molar of silver ions. Because the Kf of formation is quite large, we assume that essentially all the silver is converted to the complex and approach the problem as though we are concerned with the dissociation of silver rather than the silver complex rather than its formation. So let's see what does that mean, right? So what we have to do is, because we have such a large Kf, right? Because our Kf here is so extremely large, right? We assume that we've completely formed all of the complex. You know, we're making assumptions here, and that instead now we have, right? This is the minus Kf, the reverse equation, right? And we take the reverse equation. Whenever we take the reverse, we take the 1 over the Kf. Hopefully everybody remembers that. What is considered a large Kf? So if we go back to the tables here, you can see all of the Kfs are going to be large, right? So everything here is all extremely large. So anytime you have a Kf, it's going to be large. You can see they're all considered large. Because if you remember, most of our KSPs and our KAs are all 10 to the minus something. So whenever we're talking about KF, it's still large. Even this is, this is 1,000, right? If we compare that to, the pK of like acetic acid, I think it's 1.6 times 10 to the minus 5 or something like that. Right, so you're talking about 0.000. So 1,000 is still extremely large in comparison. So any Kf equation is going to be extremely large, and you assume that all the product is being formed. So we just take 1 over the Kf, and now you can see it looks more like a number that we're used to dealing with, right? This looks more like our Ka numbers, 5.9 times 10 to the minus 8th. And the question is asking us, what about the silver ion? What's the concentration of silver ion? What's the concentration of the ammonia in solution? So this we just set up just like a normal Ka equation. A Kc equation, right? So all we're doing is we have our ice table, right? We set up our ice table here where we know what our initial is because we made the assumption that all of this was formed 100%. We know we don't have any silver ions because we've made the assumption again that this was completely shifted all the way over to the point where we didn't have any, where the equation was completely driven over to the left-hand side. We're going to see a change that occurs, right? We know that we add ammonia into solution, right? So we've added the ammonia into the solution. So the question, if we go through here, I guess actually, I'm sorry, they were asking for silver ion. I'm sorry, I thought it was ammonia. Silver ion present, right? So I should look back. So we're trying to figure out what is the X in this equation. So we just set this up just like normal, right? We have our our equilibrium constant expression, which is the silver to the first power, ammonia is going to be to the second power, right? So all divided by our reactant. And we just plug in our concentrations. We assume, again, X is going to be very small, so the X here is going to go away, so it disappears in the denominator of the equation. And we just simply solve for X, and we find that the concentration of silver ions, or X in solution, is 1.5 times 10 to the minus 8th, which is a reasonable assumption, right? Because if we were to, look at the quantity, right? Because since the minus Kf, right, is so extremely large, since the equation is driven to the left-hand side with a very large, right? Since we have, what is it here? 1.7 times 10 to the 7th, right? 17 million for our Kf. Because our Kf is driven to the left-hand side for 17 million, you can see that if we have a 0.01 molar solution of the complex, we'd expect to have extremely tiny quantities of silver ions left in solution. Right. So amphoterism and solubility. So amphoteric oxides and hydroxides are soluble in strong acids or base because they can act as either acids or bases. So let's understand what's going on here. We have the examples are the oxides and hydroxides of aluminum, chromium, zinc, and tin. So what does that mean? So if we have our aluminum, right, they're talking about aluminum, examples. If you have aluminum hydroxide, this could be a chromium hydroxide, zinc oxide, tin oxide, things like this. Is what they're talking about, oxides and hydroxides, right? And they're going to talk about them because they have this amphoteric character, and the reason for that is right here. So it makes sense if we look at the left-hand equation. If we take aluminum hydroxide and we react aluminum hydroxide with protons with an acidic solution, the protons are going to react with the hydroxides to give us water, and we're going to have aluminum as a 3+ ion floating around in solution with whatever the counter ion, whatever X minus is the counter ion here, is going to be the counter ion floating around in solution next to the aluminum ion, right? So that makes sense. But what we're looking at here is if we go to the right, it also reacts with hydroxide ions, and it forms this complex ion. You see we form a complex ion, so the aluminum is able to react with one additional hydroxide ion to form this complex ion. And this is also going to dissolve the aluminum hydroxide, right? So initially the aluminum hydroxide is a solid. So neutral aluminum hydroxide is a solid, but we can dissolve it by adding either protons or hydroxide ions. And because of the fact that it's forming ions in solution in either direction, whether the ion is just the aluminum 3+ or the complex ion aluminum hydroxide with four hydroxides attached. All right. So one last section to talk about. I think this is we're pretty close to the last section. Will it precipitate form? To decide, we calculate the reaction quotient Q and compare it to the solubility product KSP. So if the Q is equal to the KSP, the system's at equilibrium and the solution is saturated. If Q is less than the KSP, we have more solid can dissolve, so no precipitate forms. If Q is greater than KSP, a precipitate will form. Right, think about what this is talking about, right? We have our KSP, right, is just going to be equal to the concentration of our metal ion, right, times the concentration of our anion, right? Right, and that's to whatever, x and y, right? What we're talking about is our KSP here, and if we just simply plug in Q, right? If Q is greater than the KSP, right, that means we have too much. We have a lot of ions in solution, and since we're greater than the KSP, we're going to form a precipitate. Right? If we're less than the KSP, then we can add more and dissolve it, and if we're equal, then we're at equilibrium. Right. So does a precipitate form when 0.10 liters of 8.0 times 10 to the minus 3 molar lead nitrate is added to 0.40 liters of a 5.0 times 10 to the minus 3 molar sodium sulfate solution? Like all sodium salts, sodium nitrate is soluble, but lead sulfate has a KSP of 6.3 times 10 to the minus 7. And this is, again, a double displacement reaction we're talking about here. So let's take a look at what's going on. So first thing we're going to do, we're going to determine the concentrations of all the ions just after the solutions are mixed and compare the value of Q with KSP for any potentially insoluble product. The possible metathesis products are lead sulfate and sodium nitrate. Right. What does this mean? Let me draw this out, because what we're doing, hopefully everybody remembers double displacements, right? We're reacting lead nitrate plus sodium sulfate, right? And we have a reaction occurring to give us lead sulfate plus sodium nitrate. There's going to be two of these, right? So this is just a double displacement reaction. All we did was swap the sodium ions for the lead ions. Hopefully this makes sense to everybody. And what they were saying earlier in the reaction, right? We know that sodium nitrate is completely soluble, so we know that this is going to be a completely aqueous solution. Might have some examples where we have to balance. Yeah, hopefully you can balance equations by now. I hope so. We're almost done with second semester general chem. Yeah. All right. So like all sodium salts, sodium nitrate is soluble, but lead sulfate has a KSP of 6.3 times 10 to the minus 7. Right. So we're looking at our KSP here. And our lead sulfate is what we're talking about. We have a KSP of this product on this side of the equation. And it will precipitate if the concentrations are high enough for the Q to exceed KSP. So when the two solutions are mixed, the volume is 0.10 liters plus 0.40 liters. We have a total volume, a new volume of 0.50 liters. And the number of moles of lead ion is equal to 8.0 times 10 to the 8.0 times 10 to the minus 3, and we know that because we have up here at the top, right, 8.0 times 10 to the minus 3 lead nitrate, and we know that again lead nitrate, because we know that nitrate ions are completely soluble, so we form an completely aqueous solution of lead nitrate. So the quantity of lead that's in solution is equal to the quantity of lead nitrate in solution. And so we know the molarity. So we know how, and because this was a 1 liter solution, 0.1 liter solution, we know we have 8.0 times 10 to the minus 4 moles of lead ions in solution. But then we have, since we have a new volume after we mix everything together, right? Now we have a 0.50 liters mixture. So our new concentration of lead ions is going to be dependent on this new volume. So we take our moles from there, we divide by the new volume, and we get our new concentration. So the number of moles of sulfate and a 0.4 liters, right? We know the number of moles. We can figure out, again, we were given a 0.4 liter solution. We have 5.0 times 10 to the minus 3 molar solution of sodium sulfate. So we calculate, right? We have 2.0 times 10 to the minus 3 moles of sulfate ion. We can then, just like we did for the lead, calculate the new concentration based on the new volume after we mix the two solutions together, which is 4.0 times 10 to the minus 3. And then we calculate, using our KSP equation, we calculate Q. So all we're doing is calculating, we simply plug in our concentration of lead ions, plug in the concentration of sulfate ions. We know what just do the math, you get the answer 6.4 times 10 to the minus 6. And if we go back here, oops, we see our KSP is 6.3 times 10 to the minus 7. Oops. 6.3 times 10 to the minus 7th is our KSP. So we can see that since the Q is greater than the KSP, we're going to have lead sulfate precipitating from solution. So if we go back to the problem, when we mix lead nitrate at this concentration with sodium sulfate, right, at this concentration, we're going to see a precipitate of lead sulfate crashing out of solution. Right? That's all that's going on here. All right. Where are we? Give me 1 second. We have 3 slides left. That's what I thought. Okay. All right. I'll be quick here. So selective precipitation of ions. So we can take a solution of zinc and copper, right? We have a solution of both zinc and copper in solution here. And if we add hydrogen sulfide, H2S, at a pH of 1, we see a precipitate falling out of solution. And what's happening is, in this particular equation, we're going to see the copper sulfate precipitating from solution. So copper sulfate, so copper ions, for those of you who aren't familiar, the Cu2+ ions, they're blue. So we see this blue color disappear from solution, and we have this new copper sulfide pellet that's formed at the bottom of the flask. So you can see the copper sulfate falls out of solution. We still have excess H2S floating in solution, but our zinc ions remain in solution. So all our zinc 2+ ions still remain in solution. So we selectively precipitated copper sulfide out of the solution when we added H2S. If we then filter the black precipitate off or decant away, we can then, if we then increase our pH and go up to a pH of 8, right? So if we increase to a pH of 8, what happens is a new precipitate forms. So this new precipitate is the zinc sulfide, and we're able to precipitate all the zinc sulfide from solution, and then we're left with essentially a pure water out in the end. So you can see there are ways to selectively precipitate ions from solution. This is the premise of all your water treatment facilities. So the reason that the water comes out of your tap crystal clear and it doesn't have heavy metals floating around in it is because the water scientists at the water treatment facilities are precipitating out large quantities of, or small quantities of different, heavy metals from our waters, even after they pump it up out of the ground or out of a lake or a river or stream, wherever they're getting the water from. And they are complexing or precipitating out these ions, depending on the system that they use, to essentially purify our waters, whether it's the drinking water or the wastewater. So conversely, they precipitate lots of things out of solution, our wastewaters, doing the exact same thing, and then they filter off large quantities of whatever they're trying to, get out of the water before they then dump it back into the bays and rivers or oceans or lakes, depending on where you live in the country. And that's essentially what the entire process consists of, is selective precipitation, where they don't care to get everything out, but they do want to get a lot of these toxic metals out of solution. All right. So here's another sample selective precipitation problem. All right, so a solution contains 1.0 times 10 to the minus 2 molar solution of silver ions and 2.0 times 10 to the minus 2 molar lead ions. So when the chloride is added, both silver chloride, which has a KSP of 1.8 times 10 to the minus 10, and lead chloride with a KSP of 1.7 times 10 to the minus 5 can precipitate. The question is, what concentration of chloride is necessary to begin the precipitation of each salt, and then which salt precipitates first? So if you think about from a solubility perspective, which salt is going to precipitate first, this should be an easy question to answer, right? It should be easy because of the fact we just look at the KSPs, and you can see the solubility of silver chloride is much, much lower than the solubility of lead chloride. So you'd expect the silver chloride to precipitate first. We're going to use the metal ion concentration so we can calculate what the chloride ion concentration that's necessary to precipitate each salt. The salt requiring the lower chloride ion concentration precipitates first, right? And this is, so we work through the problem. So for silver chloride, we have a KSP of silver ions, and chloride ions is equal times chloride is equal to 1.8 times 10 to the minus 10. We're simply going to plug in, right, our number. We know our silver concentration is 1.0 times 10 to the minus 2. So we plug that in for silver, and then we just solve for chloride ion concentration. So we can see the chloride ion concentration necessary is going to be just 1.8 times 10 to the minus 8. We do the same thing for lead, right? For the lead concentration, we plug in the lead as 2.0 times 10 to the minus 12. In this case, because our KSP here, right, is squared because we have 2 chlorides for every single one lead. So when we solve for our chloride ion concentration, we eventually need to take the square root, and I'm not going to go through all the math here, but eventually take the square root, and we end up with 2.9 times 10 to the minus 2 molar chloride. All right. Just actually, they're right here. So thus the concentration of chloride in excess of 2.9 times 10 to the minus 2 molar causes the lead chloride to precipitate. All right. So comparing chloride ion concentration required to precipitate each salt, we see that as chloride is added, silver chloride is going to precipitate first because it requires a smaller concentration of chloride. And, right, because we can look back here, right, that's 10 to the minus 8th versus 10 to the minus 2. So smaller chloride is required. So thus we can separate silver ions from the lead ions by slowly adding chloride so that the chloride ion concentration remains between 1.8 times 10 to the minus 8 and 2.9 times 10 to the minus 2. So we'll write our answer as concentration of 2.0 times 10 to the minus. So for this one, you would basically say, oh, I see what you're saying. So you're asking, would it would have to be, a chloride ion has to be greater than 1.8 times 10 to the minus 8th to start having some silver ions starting to precipitate from solution, right? And then in order to get the lead, you'd then have the 2.9 times 10 to the minus 2. So somewhere in between these two, you're going to have just silver ions crashing out of solution. Right, so there's a quick comment here. It says the precipitation of silver chloride will keep the chloride aqueous concentration low until the number of moles of chloride added exceeds the number of moles of silver ions in solution. Once past this point, chloride rises sharply and the lead chloride will soon begin to precipitate, right? Which makes sense, right? In the beginning, all your chloride ions reacting with your silver, and you're precipitating the silver from solution. Eventually, once all the silver is precipitated, then you're going to have a very rapid increase in chloride ions until you start reacting with the lead. All right. So there are tables here to help you understand some of, qualitatively how to separate different ions, right? So you have the solution containing unknown metal cations, right? So let's just say we had a beaker sitting here. And in this beaker, we have metal cations. We have metal plus, metal 1 plus, we have a metal 2 plus, metal number 3 with a 1 plus, and we have, I don't know, a metal 4 with a 3 plus charge. Yeah, this is metal 2. Okay. So you have all these different metals sitting in solution. What you can do is you can work through this flow diagram. So if you add 6 molar hydrochloric acid solution, so you do nothing except for just make the solution acidic. 6 molar hydrochloric acid is going to bring the pH down approximately equal to 1, right? So what happens? Insoluble chlorides such as silver chloride, lead chloride, and mercury chloride are going to precipitate from solution, right? So if you then separate the solution, separate the precipitate from the solution, you're going to have the remaining cations in solution. These remaining cations, if you then add hydrogen sulfide and either keep the solution acidic or add some more 0.2 molar hydrochloric acid to make the solution acidic, right, you're going to have insoluble sulfides that are going to start to crash out of solution under these acidic conditions, right? Copper sulfide, cadmium sulfide, bismuth sulfide, lead sulfide, mercury sulfide, arsenic sulfide, antimony sulfide, tin sulfide. So you're able to precipitate a whole bunch of new salts out of solution. Then you have additional metal cations in solution here, right? You just separate the precipitate off. You then, in turn, increase the pH to 8, add ammonium sulfide, right? So this is just another sulfide source. Instead of H2S, we're adding ammonium sulfide. And we're going to form these base insoluble sulfides, and hydroxides are going to form. So at a pH of 8, so aluminum hydroxide is going to crash out of solution. Iron hydroxide is going to crash out of solution. Chromium, zinc sulfide, nickel sulfide, manganese sulfide, cobalt sulfide will all crash out of solution. Then you have, after you filter the precipitate, you have remaining cations. And you can see here, if we then add ammonium phosphate, hypophosphate, and ammonia to the solution, we'll have
a solution of various phosphates will crash out of solution, right? So several different phosphates of calcium, strontium, barium, magnesium, all come crashing out of solution. And the only thing that's going to be left in solution here after everything is done are the alkali metal ions and ammonia, right? Our alkali metal ions, right? Sodium, lithium, potassium. Those are the things that are going to remain in solution, as well as the ammonium ion. So you can see you're able to precipitate a variety of ions by adding different reagents to the solution. And you can do it selectively. Obviously, if you were trying to purify copper sulfide and cadmium sulfide, you aren't going to be able to do it this way, right? This is not going to work because you're going to get a mixture of both in the precipitate. But if you wanted to separate lead sulfide from, let's just say, nickel sulfide, you could do that by, running these individual steps, right? So if you started off with a lead sulfide and, a lead, and you instead had a beaker here, right, with lead ions and nickel ions, right? You could just very easily separate it out, right? If you add first the H2S and 0.2 molar HCl, you'll see your lead ions will precipitate out, right? So the lead sulfide will come crashing out of solution and precipitate out in the bottom. And then you'll be left with just nickel ions in solution. Right? So then you're left with nickel 2+. And if you wanted to purify the solution, if you then add the ammonium sulfide at pH of 8, you'll see the nickel ions, the nickel sulfide will come crashing out of solution. Right, that'll form a precipitate. So you're able to separate the two out. All right. So I think that's the last slide. All right, so from, there's one quick thing. All right, in regards to questions on the exam, so we got a few minutes to talk. I would like for everyone to understand how to use this qualitative analysis of ions tables. So the stuff that we covered today, understand how to use this table here. Go through, analyze. So if I gave you a mixture of two different metal ions and I say separate the two, you should be able to separate these two different, the two different ions here. I am not going to ask you selective precipitation. I'm not going to ask you whether or not a precipitate will form. I won't ask you about amphoterism and solubility. Complex ion formation, I'm not going to ask you about. I do want you to know about how pH affects solubility. So understanding pH, so predicting the effect of acids on solubility. So you do need to understand this one. And that's where we started. So of what we covered today, this first section and the last section, I will ask, leave open for questions. But the ones in between, I will not. I won't be asking you KF, Freddie. So it's one of those things that you're really important to be introduced, which is why I covered it anyway. But it's not one of those that you're ever going to use again. But you need to understand complexes and what a complex is, because complexes happen in biochemistry all the time, just not those particular types of complexes. Help session we're going to run tonight, right? So we're running help session tonight. What time did we schedule that for? 7 o'clock. I have it written down here.
When's the test going to be open till? I originally had it scheduled. So far, I'm starting. I haven't finished writing out all of it, but I have it scheduled till 6 p.m. You were trying to understand complexes last night. Well, now you know more than you need to know. You're in good shape. So tonight, 7 o'clock, I will hold a review session for anybody who has questions. I think everybody was okay with that. Any other questions? Alrighty, other than that, no weekend test. You can do the test tomorrow. Sorry. It is sadness. Other than that, will the test be open till midnight? I wasn't planning on having it open till midnight. Right now, I had it open till 6 unless there was a reason that I needed to stay open later. It's online school, you can handle it. I'll think about it. I'll give you an answer by later this evening. You need it. Just coming off a break, you had like all day Monday. Democracy calls. Unfortunately, this is a dictatorship. Other than that, if you want to start exiting, feel free to exit. Let's see if anybody else showed up for attendance bias. I didn't see. Let's see.